we were looking at the function f of x, x times the root of 6 minus x. We want to sketch the graph of that function. We came up with the domain. We determined the terminal behavior of the function, or you also looked at whether the function has any horizontal or vertical asymptotes, and we found none. But we know exactly how the function behaves near the right-hand point of the domain at 6, and how the function behaves at negative infinity. And then we also found the intercepts, the x-intercepts and the y-intercepts, and we found 3 points, 0, 0. Actually, we found 2 points, 0, 0 and 6, 0. So at 0, 0, that's the only y-intercept, and we have 2 x-intercepts, one at 0, 0, the other one at 6, 0. So that's what we have found so far. And the next step, that was, remember, third step. That was what? That was third step, yes. And so now we look at the fourth step. And the fourth step is you want to determine where the, well, you guys reminded me after 5 minutes. Okay, so far in 1, 2, 3 steps, we looked at where the function is, what's the domain, what's the terminal behavior of the function, and the intercepts of the function. The fourth step is where we determine where the function is increasing or decreasing. Okay, and so in this step, in the fourth step, we have to look at 3 sub-steps. One is you have to find out the derivative. Now remember what the function was. The function was x times 6 minus x to the half, right? That was our function. And so what's the derivative? We apply the product rule, and we get 1 times 6 minus x to the half. So that's the derivative of the first factor multiplied by the second factor as it is. First factor multiplied by the derivative of the second factor, which would be half 6 minus x to the what? Negative half, right? Done? I still need what? I need negative 1, right? So negative 1 is the derivative of 6 minus x. Okay. At this point, how do I simplify this? Well, first of all, notice. The best way to simplify here is that I hate fractions, so let me factor out that half. Okay, which would mean that I have to multiply everything by 2, right? If I factor out half, I have to multiply everything by 2. And I also want to factor out the negative exponent. Again, I just don't like negative exponents, maybe. So I factor out the negative exponent. And so what do I have? Well, when you factor out something, right, what do you do? What do you do when you factor out something? You divide each term by the quantity that you factored out, right? So if you divide the first term of the derivative by the quantity that you're factoring out, what do you end up with? Because you're factoring out a half, right? So you're dividing this quantity by this, right? So 1 divided by half is what? That's going to be 2. And then 6 minus half divided by 6 minus negative half. Right? You're dividing this by this, right? When you divide, if you have the same base, what do? Well, you subtract the exponents, right? So you take the difference of the exponents, so what do I get? 6 minus x to the 6 minus x to the what? Half. I have negative half in the denominator, right? So it will be half minus minus half, which is what? Half plus half, which is 1. Right? So if I divide, I get that. So that's what I get when I factor out this. And from the second term, I have a negative 1 here, so let's make this guy a negative. So I'll get negative because of that negative 1. And now I factored out half, so that's fine. And I factored out 6 minus x to the negative half, so all I really have is just x left, right? Is that okay? So now, let's simplify this. Because I have a negative exponent here, 6 minus x, I'm going to write it as 6 minus x to the positive half in the denominator. And I have a 2 in the denominator. And the numerator would be what I have within the brackets. And what I have there is 12 minus what? 12 minus 3x. Are we okay with that? Okay, so I simplified the derivative. And usually, if you make mistakes in this problem, usually it is right here. When you try to simplify something, you make mistakes, and then your answers will be wrong and so on. So it's important that you do the problems to make sure you have enough practice with the algebra. And next, so this is step number 4, part A. And what is part B? Because remember, we are trying to determine where the function is increasing and decreasing, right? So the part B would be you have to find the critical points, right? So part B would be solve f prime of x equals to 0, or f prime of x does not exist, right? Can someone tell me, by looking at the derivative formula that we came up with, by looking at it, can you tell me where the derivative doesn't exist? It doesn't exist at 6, right? However, 6 is in the domain, but 6 is an end point, right? 6 is an end point of the domain, right? In negative infinity to 6. So we are going to consider 6 anyway. My point is 6 is not going to divide my interval. 6 doesn't divide my domain into anything, right? If 6 is not an interior point in the domain, then I don't have to consider that as a critical point. Am I making sense? But I mean, if you want to, you can. It just doesn't change anything. So here, the only time when the derivative doesn't exist is when x is 6. And of course, we knew that before, because the function, remember, is defined from negative infinity to 6. So right at 6, because it's an end point of the graph, you cannot have a derivative there. Now, the derivative is 0. How do I solve that? Well, if the derivative is 0, you have the derivative formula in front of you, right? What can you say? If the derivative is 0, what should be 0 then? The numerator should be 0, and the numerator is what? 12 minus 3x. And is it pretty clear that then x is 4? So we obtained exactly one critical point, which is an interior point of the domain. Okay? Is everybody okay with that? And now, what's the third step to find where the function is increasing and decreasing? Well, you are going to sketch the domain, and come up with the sign graph of the functions of the derivative function. So here is, let's say, 6, and the domain is from negative infinity to 6, so that's the domain I draw. And then I'm going to plug in the critical points, which are the interior points of the domain. So we know that the only one is 4, right? 4 is the only critical point. We also know that the derivative doesn't exist at 6, but 6 is already considered, so I don't have to. It's already plotted as the endpoint. So now I have two subintervals of the domain, right? Two parts of the domain. On each part, I have to determine the sign of the derivative function. So is the derivative positive or negative on the left side of 4? That's what we want to know. Well, that's pretty easy to determine. I mean, if you look at the derivative function, right? And what is that? The derivative function is 12 minus 3x over something. The denominator is always positive here, no matter what x is. No matter what x is, I mean, x is, of course, in the domain on the left side of 6, right? And no matter what x is, this guy, we are taking the positive root of 6 minus x. The denominator is positive. So whether the derivative is positive or negative depends on 12 minus 3x. Now, if x is less than 4, is 12 minus 3x positive or negative? For example, if x is 0, it's positive, right? So when x is less than 4, the derivative is positive. And therefore, I have positive throughout here. And then between 4 and 6, is it positive or negative? Is the derivative positive or negative between 4 and 6? So I have 12 minus 3x. You can plug in 5, for example. And do I get positive or negative? Negative. Is everybody okay? So what does it tell us about the function f? It tells us that the function f increases up until 4, and then it decreases from 4 to 6, right? Everybody's okay? So at 4, what do I have? Notice that f of 4 becomes what? It becomes a local maximum. Everybody's okay? It becomes a local maximum. Alright, so we know exactly where the function is increasing and decreasing. And now we need to know where the function is concave up and down. So that's my step number 5. And in step number 5, we determine concavity. And again, when in order to find the determine the concavity of the function, we have to look at three steps, which is, first step would be to find the second derivative. We know that the concavity depends on the second derivative. And what's the second derivative in this case? Well, look at the derivative function, and you take the derivative again. Derivative function, I think the denominator was 2 times 6 minus x to the half. So you're going to square that, right? If you square that, what do you get? 4 times 6 minus x to the... What is that? 4 times 6 minus x to the what? 1. I had a half. I am squaring that. Okay, so now in the denominator I'll get 2 times 6 minus x to the half multiplied by the derivative of the numerator, and the derivative of the numerator is what? Negative 3, right? And minus the numerator, which is 12 minus 3x, and multiplied by the derivative of the denominator. What's the derivative of the denominator? What's the derivative of the denominator? Anybody? I have a 2 there, and then multiplied by, I have 6 minus x to the half, so it will be half 6 minus x to the negative half, and what else? What else am I missing? Negative 1, very good. And then, well, I have to simplify, right, and do some algebra. And so what would be the best way to simplify here? Well, first of all, 2.5 here cancels out. And that negative 1 that I have here, let's make this one a positive here. So then I can get rid of the negative 1. And now notice that, let's see, what should I, so at this point, all I need to factor out is 6 minus x to the negative half. The same thing that I did before. So I am going to factor out 6 minus x to the negative half and see what we get. In the first term, you see that I have a negative 6, right? I have a negative 6 because 2 times negative 3 there, right? 2 times negative 3. And then I have 6 minus x, so I am dividing this quantity by 6 minus x to the negative half, right? So which is minus 6 from here, and then when I divide 6 minus x to the half by 6 minus x to the negative half, as before, I will end up with what? 6 minus x. And second term is pretty easy. All I get is 12 minus 3x. Are we okay with that? And here I have 4 times 6 minus x. And okay, so now 6 minus x to the negative half, I'm going to combine it with the denominator. So if I combine it with the denominator, what do I have? I have 4 times 6 minus x to the what? 3 half, because I have 6 minus x to the 1 in the denominator, 6 minus x to the negative half. So that negative half, I'm going to subtract from 1 to combine it in the denominator, right? Is everybody okay with that? And now, on the numerator, what I'm going to have is whatever I get from the quantity inside the brackets, and what I have there is what? Minus 36 plus 12 is what? Negative 24 minus 36 plus 12, and then I have plus 6x minus 3x, so that would be plus 3x. Are we okay with that? So that's the second derivative, okay? So that's the second derivative. Step number B would be I have to solve the second derivative is 0, or the second derivative does not exist. Again here, same thing as the endpoint at 6. The second derivative is 0 exactly when? When the numerator negative 24 plus 3x is 0, and which would tell me x is what? X is 8, right? Yeah.
Why is the denominator 4?
Because you have a 6 minus x to the negative half here, and I am, so this one has the same base, right? This is 6 minus x to the 1, this is 6 minus x to the negative half. So if I combine them in the denominator, I'll be subtracting negative half from 1, right? Is that making sense? It's like having 2 to the, let's say 4 to the negative 2 divided by 4 to the 4. You end up with 1 over 4 to the 6, right? Yeah. So, okay, now the critical point that I get here is 8, right? What's wrong with 8? Not in the domain. So I have, there isn't any point in the domain where the second derivative is 0 or doesn't exist. I mean, there is a point in the domain where the second derivative doesn't exist, which is at 6, but I'm saying there isn't an interior point of the domain where the derivative is 0 or doesn't exist. What does it tell us? Well, it tells us that the second derivative is going to be always positive there or always negative there. Okay? So the third part is I have to come up with the sign graph for the second derivative, but this is pretty easy in this case because we don't have any interior critical point here. So that means the second derivative is going to be either positive or negative throughout. And look at the second derivative formula. The denominator once again is positive no matter what x is, because it's the positive root of 6 minus x. In the numerator it is negative 24 plus 3x, right? So is it going to be positive or negative when x is less than 6? For example, I can plug in whatever I want less than 6. What would you plug in? 0. If you plug in 0, you get negative, and that tells you that the second derivative is negative throughout the domain, which tells you that our function f is what? Concave down throughout. Okay? And, or I should say like this sometimes, that is concave down throughout this domain. Okay, so that was step number 5, and now step number 6. Remember, step number 5, you calculated the critical points where you found the points where the derivative is 0 or doesn't exist. What points did I obtain? Only the interior points. I don't care about the endpoints at this point. What's the interior point? 4, right? So I need to know the point corresponding to 4. So I need to know what is f of 4. What is f of 4? What function is f? F is the original x times root of 6 minus x. I have to plug in 4 there. If I plug in 4 there, what do I get? 4 times root of 6 minus 4, right? 4 root 2. 4 times root 2. And then we have couple of intercepts, right? What were the intercepts? So I get this point, right? I get the point 4 times root 2 on the graph. I have the intercept 0, 0. I also have the intercept 6, 0, right? That's the point corresponding to the endpoint 6. These are points on the graph. I didn't get any points from the 5th step, right? At the fourth step I got the number 4, but at the 5th step I didn't get any interior critical points, right? So if I had one, I would have to compute the corresponding point. So the first thing I'm going to do now is plot these points and then come up with the graph. So let's do that. What is the approximate value of 4 times root 2? What's the approximate value of 4 times root 2? Okay, so let's draw our x-axis right here. Let's draw our y-axis right here. Okay, maybe I'll draw the curve with this color. So we have a point at 0, 0, right? So that's this one, let's say. And let's say this is 1, 2, 3. No, let's just say this is 2, this is 4, and this is 6, okay? This is 6 and this is 4. At 6, we get the point at 6, 0, right? At 4, what's the point? 4 times root 2 is the height. What is that about? Anyone has that number? 4 times, what's that? 5 point? Okay, about 5.5. So let's say that height would be 2, 4, 5 right here. So that's the point corresponding to 4. So this is the point 4, 4 root 2. And now we have to sketch the curve with the graph. So what should I do? Well, I start with the leftmost point that I have now. I need to know what is happening on the left side of this point, 0, at 0. We are going to use the increasing, decreasing behavior and the concavity. On the left side of 0, what is happening? Is the graph increasing or decreasing? On the left side of 0, is the graph increasing or decreasing? Look at the sign graph for f prime, right? We said that the function is increasing up until what? 4. So on the left side of 0, the function is increasing, right? On the left side of 0, the function is increasing. We know that the function would be concave down there, right? In fact, we know that the function is concave down on the entire domain. So I know that the function is increasing concave down. Now, it is increasing, but it is increasing from where? Remember, we determined what is happening at negative infinity. At negative infinity, the the value goes to negative infinity, right? So it's coming from down, it's going up, right? It is concave down. Sorry, I have to be a little careful. I have to come. Okay. So this is. It is concave down. It is increasing up to this point. What is happening up to 4? It is still increasing, right? Up to 4, it is still increasing concave down. So I guess it is still increasing concave down. And then after 4, it is decreasing and concave down. So I know it looks like what? Like this. So that's how the graph looks like. After all that work, we get a very simple curve. But that's usually the case. Okay. Any questions on this? If every time you have a problem on sketching the graph of a function, these are the steps that you need to follow. Okay. Everybody has a copy of the 2 handouts. Okay. There are 2 handouts. One of them is a problem from section 3.1. It is asking you to find the absolute maximum, absolute minimum of a function on a given interval, which is a closed interval. And the reason I'm giving you this handout is that I want to make sure that everybody knows what are the steps to find the absolute max and min of a continuous function on a closed bounded interval. I usually ask this question, okay, in the third exam, and so you should know how to do this problem. So anytime in the homework when you see a problem like this, you follow the same steps. So you should do this when you are having dinner or lunch. Make sure that you know what are the steps. Okay. There is another handout. And in the other handout, remember we talked about the first derivative test and the second derivative test. So in this handout, ignore the fact that I write section 4.3. It should be 3.3. The reason it's called 4.3 is because when I made these notes, Stuart's calculus text, the section numbers were different. In any case, just make it 3.3. The first derivative test, I wrote down what is the test. Okay, I explained to you how the test works by example, and then I give you an example here, and I ask you to follow certain steps in order to use the first derivative test to come up with the local max, local mean values. Right? Is everybody okay? On the opposite side, you have the second derivative test. I state the second derivative test there, and then I give you an example again. and I ask you to use the second derivative test to actually I work out and the problem, but those are the steps that you need to read and make sure you follow those steps when you do your homework problems from that section. Okay? Is everybody okay? So whatever you need to solve those problems you have in these handouts from section 3.3, there wouldn't be any reason why you won't be able to do this type of problems in the exam. Okay, so that's that. So we are done with section 3.5. Remember the video that I sent that has another example on sketching the graph of a function. Am I making sense? Yeah.
Is that all it has?
In section 3.5?
In the video.
Oh, in the video, the first part is on section 3.5. The second part is on section 3.7, which I haven't talked about in the class. So you can look at those examples. 3.7 doesn't have any theories, just like 3.5 doesn't have any theories. We are just using whatever we learned in 3.1, 3.2, and 3.3 in section 3.5. Same way in section 3.7, these are applied problems, application problems, and we are going to be using what we have learned in 3.1, 3.2, 3.3. So these are just problems, and you just have to. I have 3 problems that I work out in that video, so you can look at those examples, and before you do the homework problems from 3.7. But I will be doing other examples from that section as well in the class tomorrow. What was I going to say? Tomorrow's quiz will not be in the class. I need the class time, unfortunately. But you will be taking the quiz online on WebAssign, and it will be due on Sunday. As soon as I finish this chapter, I think the date was right before Thanksgiving, right? 21st? Yeah. So 21st is right before you go for Thanksgiving break. What is that? And what would be the waste though? Everybody gets an A. I heard a story that somewhere some time ago there was an instructor who used to give all A's, right? And then the administration said, no, you cannot do that. You cannot give everybody an A. So then he said, well, I'm going to give everybody a B. So he gave everybody a B. I'm not sure if it is true, but I heard that story. No, not here, but somewhere else.
So bad. That's
Okay, so since what I'm going to do now is go over one more example, and so the example that I want to do now is so right now the example I will be doing is from section 3.3 and also from 3.5 at the same time. So this is example. Suppose that I have the function f of x, and I have that this is x over x squared plus 4. And there are a couple of questions that I'm going to go through. The first question that I ask is, what's the domain of the function? And what would you say? You can just say it, right, by looking at the function, what the domain is. because the denominator, no matter what x is at least 4, right? So the domain is all real numbers. Okay, so that's the first question. Find the domain of the function. The second question that I want to ask is find the horizontal and vertical asymptotes of the function, if there are any. That is, or determine the terminal behavior. So this is where you determine. Determine the terminal behavior. And at the same time, you will see that when you try to do that, you will come up with whether you have any asymptotes. Okay, any asymptotes. And well, terminal behavior means the domain is from negative infinity to infinity. So I want to know what is happening at infinity and what is happening at negative infinity. So that means I want to know what's the limit of the function as x goes to infinity, and what's the limit of the function and as x goes to negative infinity. What's the function? This is x over x squared plus 4. What is that limit? Well, what's the limit as x goes to infinity of x over x squared plus 4? Remember what I said about rational functions. When you are interested in the behavior of the rational function when x is big, only the dominant terms matter. So the dominant terms are x over x squared. X over x squared is 1 over x. And the limit of 1 over x as x goes to infinity is, the limit of 1 over x as x goes to infinity is 0, right? The denominator is going to infinity, the numerator is 1, right? You're dividing by bigger and bigger numbers. The limit will be 0. So I know that the limit of this guy is what? 0. And so I know that y equals to 0 is a what? So what does it mean when I say that the limit at infinity is 0? It means that as x gets bigger and bigger, the graph of the function, the height of the function is going to 0, right? Remember, the value of the function is the height of the graph of the function, right? So as x goes to infinity, the height of the graph is going to 0. So that would mean that you have a horizontal asymptote at the height y equals to 0, right? What is y equals to 0? Well, y equals to 0 is exactly what? The x-axis. So that's a horizontal asymptote. This is a horizontal asymptote. And if I look at this guy, it is also 0. So I don't get another horizontal asymptote, okay? Now, do I have any vertical asymptotes? No. Remember, a rational function is continuous in its domain. Domain is everything, so there couldn't be any vertical asymptotes, right? If you have a vertical asymptote, then the function would be discontinuous there, right? So I don't have any, so none, no vertical asymptotes. Okay, so that's that was what, 2 or 3? 2. Okay, 3. Find the intercepts of the function. How would I find the? Remember, okay. What is our function? Our function is x divided by x squared plus 4, and I'm going to denote the function by y. In order to find the y-intercept, you are going to set x to be 0, and then if you set x to be 0, and then you solve for y, and what do you get? If x is 0, then y is 0. And for the x-intercept, for the x-intercept, you are going to set y to be 0, and then you need to solve for x, right? So that means y is equal to x over x squared plus 4, and if that is 0, remember y is equal to x over x squared plus 4, and so you set that to be 0, and that tells you x is what? Zero. And so what is the x-intercept? 0, 0. What is the y-intercept? So I have only one intercept. Okay, very good. So then are we done with that? Question number 4. Let's say the question number 4 says, find the critical points of the function and classify them by using the first derivative test. Okay. Again, remember, I'm trying to do 3 and 3.5 at the same time. So in part 4, question number 4, so let's say you are asked to find the critical points of the function f and classify them. What do I mean by classify them? You need to determine whether at each critical point you have a local max or a local min. Okay, so again, what would be the steps here? Well, you have to find the derivative first. And if you find the derivative first, what do? Well, you just apply the quotient rule. So apply the quotient rule. What do you get? You get x squared plus 4. You square the denominator. Look at the function f. And what's the here? Well, this would be the denominator multiplied by the derivative of the numerator is 1, minus the numerator times the derivative of the denominator is 2x. And if you simplify that, you get negative x squared plus 4 over x squared plus 4 squared. Notice that you cannot cancel out. I mean, you might overlook that. Sometimes students make a mistake that they will say, well, x squared plus 4 and x squared plus 4, they cancel out. But this is not negative of that whole quantity, right? This is just negative x squared plus that. This is 4 minus x squared, not 4 plus x squared. Okay, so be careful with that. You cannot cancel out here. And so that's the first derivative. And then I need to solve for the critical points, right? So solve f prime of x equals to 0, or f prime of x does not exist. And in this case, well, you look at the derivative formula, right? Can you give me a value of x where the derivative doesn't exist? No, because the derivative is defined for any x, because the denominator in the derivative formula is not going to be 0, no matter what x is. So I get no solution from here. And from this guy, what can I say? If the derivative is 0, what should be 0? The numerator of the derivative should be 0, right? Which would be negative x squared plus 4 would be 0, and which would mean that 4 minus x squared is 0, which would mean that 2 minus x, 2 plus x is 0, and which would mean that x is 2 or x is negative 2, right? So I get two critical points. They are both in the domain. So I have two critical points. And now I need to know, I have to classify the critical point, right? Do I have a local max or a local min at each of them? I forgot to say, by using the first derivative to classify them, if you don't mind, I want to add something here by using the first derivative test. Okay. And so how do I apply the first derivative test? Well, very simple. I draw my domain, draw the critical points, -2, +2, but the critical points divided the domain into 3 parts. On each part, I need to know the sign of the derivative function. What was the derivative function? The derivative function is right here, right? And look at the derivative function. If x is less than -2, is it positive or negative? It's negative. When x is less than -2, you can ignore the denominator here because the denominator is necessarily positive. So ignore that. What's the sign of the numerator when x is less than -2? Well, when x is less than -2, like -3, this guy would be bigger than 4, so it's negative. When x is between -2 and 2, for example 0, it's positive. When x is bigger than 2, again negative, right? When x is bigger than 2, for example 3 squared would be 9, -9 plus 4 would be negative. So I can come up with exactly where the derivative is. Did we say negative here? Positive, negative, which means that our function f, so this is the derivative function, and our function f then would be decreasing here, increasing here, and decreasing here. So at f of -2, what do I have? I have a local minimum, and at f of 2 is my local maximum. And we are out of time. Okay. The fourth problem that I wanted to do is solve the same problem by using the second derivative test, but we will finish it next time.